of y is equal to f of x, and where there is x in our f of x, we are replacing it with x. The function will remain f of x. And now, if we have our f of x, right, and we replace f of x with the x plus h, it simply means our y at that point is going to be f of x plus h. So which means, if I'm to ask you what are the coordinates at point A and what are the coordinates at point B, what will you say? Mm-hmm. That's true. And at B, it's x and f of x. That's very correct. So which means if I said find the gradient using that same thing, what will you do? Using those coordinates. Yes, find the gradient of AB. Actually, now we cannot call it the gradient. Actually, it's the gradient, but they use another term. They call it the quotient, the difference quotient. They call it the difference quotient. We would say y1 minus y2, which is f of x plus h minus f of x all over x plus h minus x. That's why they call it the difference, because we are subtracting the difference quotient. Quotient is the answer we get after we divide. So we are subtracting and then we are dividing at the same time. That's why at this moment it's called the difference quotient. Are we together? Now, there is this thing that I want you to look very carefully. The gradient we calculated is an approximate of an AB, and we are approximating that this is the rate of change of speed of Usain Bolt during that part AB. Why I choose that part is because it's the steepest part of the graph. And this is the middle of the graph, which is assumed to be the second and the third quarter of his race. Therefore, we simply mean that way he had the highest speed. So the gradient is very high there, it's very steep. So which means if we want to find the exact gradient, we have to move closer to the point we want. So let's say we want gradient at point A exactly. Do you realize that the more I'm moving closer to that point, my h is approaching to be 0? Because look, every time I'm moving up to this point, my h is becoming less. Every time I'm moving up, my h, you see, my h is now this distance alone. It's getting smaller. So which means the more closer I become to the point that I want gradient, which is point A in this minute, until I reduce the same white line to fit exactly, this is my point A. If my line fits, or if my triangle fits exactly inside the point that I want gradient on, is as good as my h is 0. But remember, my h here is a denominator, because if I'm to simplify this difference quotient, I'm going to see that my difference quotient is going to be f of x plus h minus f of x all over, this is x minus x, so I'm going to left with h alone. So which means if I'm moving closer to the point that I want, my h distance is becoming so tiny, it's becoming very infinitesimal small. It's very, very small. You get the sense that it's a value that we cannot count on because it's 0. But definitely we can't say it's 0 because it's there. You get the sense? It's there. So which means we're just going to say there is a limit that h is going to be. We said it's approaching 0. We can't say it's 0. You get the sense? So which means now we are saying our difference quotient of the exact distance of the exact point that we want is the limit h approaches 0. As h approaches 0, our f of x plus h minus the f of x all over h